This is Reid. He's going to talk about Visual Studio and C++ and Windows. So,
Hooray. All right. Hi. Yeah. So what I want to work on is I'm basically working on bringing Clang and LLVM to users of Microsoft Visual C++. My name is Reid Kleckner, and I work at Google, and I work on a team of about 5 people, some of whom are here currently. Hans, and I don't see anybody else, but yeah, you give lots of good advice. But anyway, so C++ developers, they want, they have high demands for toolchains these days. They want you to be able to compile their code, make it go fast, and they want you to do it quickly so it comes back to them. And then, when they have bad code, they want you to tell them what it was that they did wrong with helpful diagnostics or, more powerful static analysis and things like that. They also like things like dynamic tools like AddressSanitizer, which is one of Clang's more interesting features. And they're also hungry for new C++ language features like C++14, which I'm told Clang and libc++ together actually support as of today. So thanks.
As of last night, but
yeah.
close enough.
I thought I saw some commits from Faisal for whatever, lambdas. Anyway, so we have all these things, but we only have them on Mac and Linux, and why can't we have them on Windows? So it'd be really nice if we were able to support that. So what do we need to do to get there? So the biggest barrier is that you really have to be able to integrate into the existing platform. There's a lot of libraries on Windows, and they all have this ABI. And if you want to compile your code with Clang, you need to be able to support that ABI so that you can link against system libraries like just the standard library that everybody's using, or just external libraries, things like that. And you really want to be able to produce an application that is indistinguishable from one that the Microsoft compiler might have produced. End users shouldn't care about this kind of thing. Shouldn't be visible that you've got other funny DLLs present, doing emulation or that kind of thing. It should just really be the same application at the end of the day. And I think most importantly, your compiler is your toolchain is going to need to integrate into the existing development environment. And basically on Windows, that means Visual Studio, and you really need to integrate deeply into that IDE. So the ABI compatibility is really important. I just sort of want to walk you through why. If you don't have ABI compatibility with the existing Microsoft C++ toolchain, then you can't use all the standard C++ libraries that they ship, or at least some of them, like ATL and MFC and the standard template library. All that stuff exposes a C++ interface that is locked into the Microsoft C++ ABI. So you won't be able to link against any of that. You also won't be able to use any third-party C++ libraries or DLLs. You're going to be restricted to extern C and COM interfaces. And if you want to wrap some language feature that only Microsoft supports, like say C++ CX, you're going to have to build an extern C or COM interface around this, just so that you can, with your different ABI, interact with that code and get access to it. And this is a big headache. And so, like, just supposing that you even already had the source code for your entire application because you're lucky, you're going to have to port that code. And even if you have the code, you may not actually own it. And you might say that standard libraries are standard, like you should be able to port from one standard library to another. If anybody says that, they clearly haven't actually tried it because they're not very easy to port between. And the really big thing is that you have to do all of this before you can even try your alternative toolchain, right? Nobody's going to try out Clang if they have to first port their entire set of third-party dependencies over to a new compiler. They can't even play with it and just do a baseline comparison. So the ABI compatibility is really important. And the other thing that is really important is Visual Studio support. Visual Studio is really the bar for IDEs that other IDEs are compared to. It's sort of really the first in its class, and you can't you can't come to real users on Windows who are used to using Visual Studio and tell them that, if you should try my compiler. Step one is write a makefile and run make, like from an 80-column, CMD window. That's just not going to fly. So you really need to integrate. And so these days we have that. We have Clang CL as a front end that provides some command line compatibility. That's mostly thanks to Hans. And we also have some command line compatibility for LLD, which is LLVM's linker. And at the end of the day, we get this nice integration where what we'd really like to be able to do is just have drop select menus where you can just activate Clang features, like right next to the standard build configurations like debug, release. You just have like AddressSanitizer build, and done. You can find bugs. At the end of the day, the picture should be that Clang and LLVM are integrated into your development environment, just like we want. So how are we going to get there? We have to overcome a bunch of challenges. The C++ ABI is not documented. There is no, paper ABI, no System 5 docs that will tell you what the name mangling scheme is for Microsoft C++. The file formats were a little bit better off. There is a sort of a COF standard. It did come from old Unisys. But it's still kind of a moving target as Microsoft, adds new features, managed code, things like that. Stuff changes. So it's a little bit of a moving target. And other things, we need to be able to parse, a variety of system headers that have a lot of language extensions. And then, language extensions aside, there's lots of fun, C++ templates that have, interesting invalid C++ code that just happens to compile with the Microsoft compiler. So we have to be able to understand that. One other challenge that we had to overcome is that, while Clang is already sort of a production, compiler, we also wanted a linker, and PE-COF support was sort of entirely just stubs in LLD. It was just had to, fill in the blanks there. And so Reid's been working on that. Most of my efforts have focused on the C++ ABI support, and that's mostly in Clang. So that's what I'm going to talk about mostly. So what's really in a C++ ABI? C++ ABI is basically everything you need to know about in order to interact with C++ code across a translation unit boundary. So that means things like name mangling. C++ supports overloads where you can have two functions with the same name, but they're different functions, and you can call them based on the types, static dispatch, all that good stuff. You need to be able to come up with different symbols, so you have different symbols for those two overloads. And then there's a pile of other stuff that makes sense, like you're laying out records. Where exactly do you put the virtual function pointer? How are you going to pad things? This could be different. And then I think bit fields are the most interesting point of compatibility. How exactly do they get packed? Do they get packed at the beginning, the end? It's good stuff. And then it just goes to the long tail of sort of like arcane C++ things, like how are you going to prevent double initialization of static data members of class templates? You need some scheme to do that, and you have to implement the ABI scheme. And at the end of the day, this stuff all matters. So how do you test this to figure out that you're actually doing it right? So what you end up doing is writing a bunch of basically compiler A/B integration tests, where you take a source file like this, you have a common header, and then you have an if-def with two sides of the if-def. One bucket is one translation unit, and the other is the other translation unit. Then you can run compiler A and compiler B on the translation unit twice, link it together, run it. It should probably exit 0. If it doesn't, or it fails to link, then there's an ABI problem. And so in this example, what I'm trying to do is I want to see that I can pass the struct s by value to the function foo, and s is just a 4-byte pod little struct, no big deal. And when I pass it to foo, I should really get the value, the data that I put into s on the other side. Otherwise, failed test. And so to implement this kind of stuff in Clang, the Microsoft compatibility really sort of affects all the layers. I'm not really going to talk about the parser and lexer layers. Those are sort of more for handling things like language extensions, like UUIDEV, the template parsing. That stuff's kind of fun. Just simple decal specs for DLL export. Those are all fall under the category of extensions. they're part of the ABI, but not as much. Most of the work that I work on is in the AST and CodeGen layers. And so the AST layer is basically a library that has all of the stuff. It's first and foremost, it's all the data structures that represent C and C++ and Objective-C code in Clang. But after that, it's got sort of all of the LLVM independent features that you need to think about when representing C and C++. So you really need record layout in there because when you're doing template instantiation, you're going to need to be able to answer questions like, what is the size of this object? And that is really an ABI question. And then furthermore, offset of and align of. And then you also have other stuff like the name mangler and vtable layout code. That's really in there just because it's sort of LLVM independent. And then you have other stuff which is very integrated into LLVM, and that all lives in the CodeGen layer. Although it's not clear, maybe perhaps it should be called IRGen, but that is hard. Yes, naming things is hard. So it is Clang CodeGen, and that is where we do things like lowering virtual method calls, figuring out how we're going to represent member pointers because there's a whole bunch of decisions there that you have to make in the ABI. One of the things I'm going to talk about later is doing pass by value. This turns out to be very complicated. So as a result, most of the things that I work on are in CodeGen. But in the process of adding compatibility for this ABI, you always end up hitting corner cases because we're trying to write a compiler that's compatible with something that exists. We don't have documentation. The only thing we can do to figure things out about the ABI is write tests. And so I think it's possible that we end up writing more tests than the people who are actually implementing this in the first place, because they were taking user code and running that, and that's sort of a certain kind of code. And then if you're a compiler writer trying to write tests to figure things out, you write different kinds of code. And so we sort of hit untested dark corners. And we get fun results like just crash on valid from MSVC if you instantiate a template with a null member pointer, or just getting invalid cough back, or taking perfectly valid C++ and the ABI makes it impossible to actually compile that correctly. In particular, just member pointers are an area that are very different from what standard C++ is, so you can get lots of fun bugs there. The first and most basic part of the ABI, though, is basically, I want to say name mangling. And so I kind of want to walk you through that for a flavor. To start off, Microsoft uses a question mark prefix, and that's sort of the identifier for, this is going to be a C++ identifier. Let's demangle, keep reading it as a C++ identifier. And Itanium, and they use a lot of characters that are not valid C identifiers, which is an interesting design choice. That's just fine with cough. Itanium, on the other hand, is sort of it's more portable because it's a C++ ABI that's designed for many targets, many object file formats, and so these identifiers are very, very simple. And they have the _Z prefix, which you are probably familiar with if you've been staring at link errors. Then there are a whole bunch of other just basic decisions in the ABI, like we have this symbol, foo, which is inside of a namespace space. So we're going to mangle a namespace into the symbol. Where does it go? Well, in the Itanium ABI, you kind of do things from the outermost scope inwards. So namespace goes first. In the Microsoft ABI, the symbol comes first and the namespace comes afterwards. Yeah, same point. Symbol comes first for Microsoft. And then, to handle overloads, you have to take the parameter types, mangle them in there somehow. And this all makes sense, right? This is like basic stuff. Doesn't matter what your character codes look like. This shouldn't surprise anyone. But then you start hitting corner cases on fun C++ features like static locals. And the basic problem here is that the obvious way to mangle a static local is to take the name of the function that it's enclosed in and somehow combine it with the name of the variable. This should be pretty unique, right? But it turns out you can redeclare variables in different scopes. And so you have multiple static locals with the same name. Okay, so now I need to number them so I can differentiate them. And this becomes part of the ABI, unfortunately, this kind of really detailed stuff. And so Microsoft uses a scheme which, as far as we can tell, it's just you number the scopes in which you can declare variables, and you use that number in the name, and we're good. Yeah, so you just count the number of scopes you enter, and then you use that count when you encounter a static local. However, it turns out that you can declare variables not at the top of a scope, right? And so counting is not really enough to do this right. And so in this test case that I think it was David Mainemer came up with, you declare two static locals with the same name, they get the same mangled name, and this is fine. The compiler is fine with this. It generates cough, but the linker says because these end up getting put into comdats, the linker sees two comdats that have identical keys because the mangled name goes into the key, and then the linker just says, "You just gave me invalid cough. I don't like that. We're done." And so this is the first WAT moment. This is perfectly fine, but totally unexpected. Or it's not perfectly fine, but there are bugs. But anyway, another area of sort of corner case of the ABI is unnamed structs. And I guess it sort of makes sense that things without names are kind of hard to work into your ABI, but they show up in places. So it appears that Microsoft basically somewhere early on they give the name bracket unnamed tag to unnamed structs. And so if you write code like this, for example, where I have an unnamed struct with a method f, where I then try to access a member g, the compiler will tell me that g is not a member of unnamed tag. So that's really what it thinks of as the name of the struct. And this actually shows up in the ABI. You can, if I create a struct, foo has a virtual method f, okay, so that gets a virtual function table. I can actually create unnamed structs that inherit from foo and override f with my functions that print a and b. And there's not much I can do with this struct besides declare some variables or maybe declare a type def, but in this case I'm going to declare some variables. And then I had to use this call foo indirection, otherwise the calls get devirtualized. But if you do this, then this program ends up printing B twice because the name of the VF table is just under 7 unnamed tag. And we get 2 VF tables, and one of them wins. The compiler just throws out A's VF table, and we get 1 VF table. And so we get B twice. And it's flat. Okay. So another area of the ABI that is interestingly different is the way that they do virtual tables. So Itanium and most ABIs, I think this is actually part of the early papers that Bjarne wrote about C++. He was saying, look, it's so easy to implement virtual inheritance. We have the virtual function table, or we have the virtual methods. They go into a table in the way that you would expect. As you inherit and you add more virtual methods, you append to the table. It's great. It works. And as you inherit virtually from new virtual bases, we just have a table that grows backwards, and new virtual bases get added to the top of this table as we add more bases. For various reasons, Microsoft does something slightly different. They do not have one table. They have 2 tables. One is the virtual function table, which corresponds to the VF pointer here. So the VF pointer is pointing at a table full of function pointers. And they clearly know how to address things at negative offsets because RTTI lives before the virtual function pointers. But for whatever reason, virtual bases are stored separately. And so if you have any virtual inheritance in your C++ class, like I do here, where I inherit virtually from A, then I have a separate table with a separate VB pointer, and that grows forwards. Yeah, but otherwise, the high-level layout rules are kind of the same for object layout. This is just the classic, C++ diamond inheritance problem and how you solve it, you've got this shared base A, B inherits from A, C inherits from A. Okay, well, when I do multiple inheritance of B and C, I want to make sure I only have one copy of A. So I use virtual inheritance on A, and then I get this layout where I've got my non-virtual bases first in the standard order, left to right in the inheritance graph, B, then C. Then I've got my fields, and then I've got all my virtual bases at the end. And this is basically the same. The only difference here is that instead of having a virtual table pointer, I've got a virtual base table pointer. It's slightly different. But then this leads to other fun things, as you have this VB table pointer in the middle. I guess this isn't that example. But yeah, so there are other interesting differences. I can only assume that this has something to do with interacting with COM, because basically the layout here that I get from Microsoft Visual C++ is I have the virtual function pointer, then I have 4 bytes of padding because I need to align the fields of the A subobject to 8 bytes because it's got a double. But I end up with a whole 8 extra bytes of padding here that you sort of wouldn't expect. You would naturally assume that we go VF pointers 4 bytes, then the integers 4 bytes, and the double is 8 byte aligned. Like that makes sense. But it looks like they're doing something like this, right? You could access this in plain C if you declared some structs like this, and this would make a little bit of sense. But again, no documentation, so these are things we figured out experimentally. So one of the other sort of interesting corner cases that comes up is C++ tells you that you're not supposed to have objects of the same type alias. If you inherit from something, then your primary virtual base is at the same, you have the same this pointer, you share this pointer. But if you have multiple inheritance, then zero-sized objects should not alias. They get 1 byte of space essentially, right, to space them out. But this does not happen in the Microsoft C++ ABI. And you can come up with contrived corner cases like this, where I have like 3 records that are all zero size, or well, they have no fields, 2 of which are zero size. And I've managed to get the virtual base A of C at offset 4, and I've managed to get my non-virtual base A through B at offset 4. And this is not supposed to happen. Yeah. Anyway, so those are some interesting parts of the C++ ABI. Just test cases we wrote, things we discovered. But I think the thing that I'm currently working on is basically passing C++ objects by value. And this is sort of a really hard problem I've been spending a while on, but I'm sort of going to walk you through it. So how do you pass objects by value in C? So the basic thing you do is you just put, why not just put the struct right on the stack, just like you would in a normal, plain C calling convention. Everything goes on the stack, right? Right to left. So in this example, I've got my struct A, which contains 2, and I just push 3, somehow get 2 onto the stack in that location, then push 1, and make the call. That's the sort of the C way of doing things, right? Okay, well, in C++ things are more complicated, right? Because I can't just copy my struct A onto the stack. That's not okay. I have to actually call the copy constructor. And so, Itanium has a solution where they say that if you're passing a C++ object that has a non-trivial copy constructor, by value, then it's at the ABI, at the sort of binary level, it's not really being passed by value. You actually get this hidden pointer. The caller creates a temporary somewhere else in the stack, and then it creates a pointer to that, and then it manages the lifetime of the temporary. And so I get something like this. In the Microsoft C++ ABI, you can probably see where I'm going with this, they did the C thing, right? So if I'm passing this by value, I construct A of 2, and it just goes right in there with the argument slots. And this is awesome. And then also, I guess, one thing that's worth noting is that the 2 object, the A object, is actually destroyed in the callee. the lifetime of that object becomes part of the callee. And so I'm going to sort of walk you through this because you might not see the problem here yet. This is how you might lower this calling convention. It might be a natural way to do this in x86 assembly. I just came up with it. Basically going to push 3. I'm going to create some stack space, right? It's 4 bytes in this case. I'm just going to take the address of that stack space, go off, call my A constructor, right? Come back. Okay, when I've come back, I've got 2s on the stack, should be initialized just like it should be. And then I'm going to keep going in the call. I'm going to finish the call just like that. And so we hit this problem that you can't represent this in LLVM IR because looking at this, calls in LLVM IR are single instructions. They're not divisible, right? There's no way for me to get access to that piece of the stack in the middle of the function call. And so what we do today is completely wrong. What we do today is we lower down to calling foo and we use the byval attribute, which implies just a straight up memory copy. And we're not calling the copy constructor, and this creates problems.
And you absolutely have to call the destructor afterwards.
We call the destructor in the callee on the copy anyway. And most of the time this is okay, because if you're passing something like a very simple implementation of standard vector, then you only destroy one version, and so long as your object does not reference itself, right, then everything is fine. But it's still a miscompile, right? And so essentially this breaks down when you do something like if you pass small vectors by value, or your standard library string implementation happens to be a small string like it is in libc++, then you're hosed. And so this is a big problem. So how are we going to do this? This is what I've been thinking about for a while. So some of the things some of the challenges that you need to think about are calls can be nested like this, right? All of these can be passed and be returning things by value. And the stack space that I use for that can't overlap. And how do I tell LLVM's optimizers that, if I want to take the address of the outgoing argument, how do I tell it that you can't move loads and stores across these boundaries, even though, as far as it's concerned, they don't necessarily alias. And so basically, we have to come up with some solution where, if I'm going to do this nested call, I need to allocate some stack space to start creating my value, and then do stack adjustments, which is completely not part of what the standard LLVM code gen flow does today. We have this nice level stack pointer where arguments, are stored onto the stack at offsets, and then we just make the call. Another thing you have to think about is that a lot of people propose when they see this, they're like, oh man, can we just tell LLVM that don't call memcopy, call my copy constructor. I'll just give it to you somewhere, right? And the problem here is that any constructor can throw exceptions. I mean, the first problem is that you would be failing to perform copy elision, which would be bad. Your users probably don't want that. But even if you did that, then LLVM would be responsible for figuring out what happens when one of these copy constructors throws. It's going to be lowering that down to something like an invoke, and then that's not so good. So we need to have a solution that can, sort of bound the lifetime. And one other thing you need to be able to do is, if you throw, you need to be able to clean up the stack space that you've allocated to perform this call without actually hitting the call. So that needs to be a little bit independent, at least. And any design that we come up with should really be amenable to, if not an efficient lowering today, it needs to work sometime in the future. We should be able to optimize it to something that doesn't use a frame pointer, that just uses constant stack adjustments. And so the proposal that I've been talking about at Google with a variety of people is basically an inalaka attribute. And I'm open to other suggestions. This is the leading solution for the moment. And it would basically come down to a lowering like this. And the idea is that you use the alaka to take the address of the outgoing argument slot, and you are passing it by a value in the alaka. The alaka is the value. It's in the alaka. And to sort of bound the lifetime of these things, in order to implement cleanup, you'd start off with something like stack save, stack restore, which are kind of, right now they're ugly ducklings of LLVM IR, but we could teach backends to be smart about that, or come up with other solutions. But this would be something that we could start with. And then this is an example of sort of how it handles something like a nested call, where I've got my A constructor, which is for whatever reason taking an A by value. I do my outer stack save. I allocate stack space for the outer argument. I do my inner stack save. I allocate stack space for my inner argument. I construct my innermost argument, call my inner function call with the inalaka parameter on A2, and then I clear the stack back to where it was before I was going to do the call to foo. And then I can do the call to foo, passing the address of A, inalaka on the stack, and then clear everything off. And then this is an example of how you would handle exceptions. So basically using I guess it's just a single, no nested. But if A were to throw here, I've adjusted the stack to allocate space for it. But then suppose that A's constructor throws an exception, then we would go to label LP, skipping foo, and we would need to restore the stack back to where it was before I did the alaka. Oh man. So yeah, and eventually, this stack save restore, right now it's not very efficient. It basically implies that you're going to have a frame pointer. You're doing evil things, and the optimizers will look at you askance. But it's possible that in the future we could optimize this for certain regimes of calling stack save and stack restore, or we could do something crazy like A-free or FREA. I don't know what people think is best, but we don't need to solve that problem today. I think inalaka can work without that. At least we should not be miscompiling small vector. Anyway, so that's kind of my talk. Basically, we are working on integrating Clang and LLVM into Visual Studio. We are trying to get the ABI support so that you can link code compiled by Visual C++ with code compiled by Clang. We want to get certain amount of extensions into Clang so that we can actually compile real code, use ATL and MFC headers. And we're discovering a lot of corner cases. And the big thing is we need to figure out how we're going to do passing things by value. But yeah, so any questions about that?
Any questions at all? Use the mic. You can all also stand here and figure out exactly how crazy Reid is.
I'm just curious what you plan on doing. It's unrelated to what you've talked about. What you plan on doing about debug info?
Debug info. So yeah, debug info is PDB is like the least the file format that Microsoft uses for storing debug information, and that is the least documented thing. We haven't looked into it, we have, but we're not going there yet, or. Our sort of leading proposal for getting a good debugging experience on Windows is to use LLDB and Dwarf to write a plugin for Visual Studio and probably also WinDBG, because that is a very important debugger, it turns out. And teach that basically how to read Dwarf. And we believe that this is actually doable because people write debuggers for Visual Studio for their embedded targets. This is actually something that there's a plugin API for. And we've heard of people doing it elsewhere, so should be workable.
Yeah, he got to my second question first. And I'll tell you, yes, PlayStation, we have a debug integrated into Visual Studio for debugging on the target.
Cool.
The question I actually care about more is this C++ ABI testing thing, is that like in the tree public?
So it is not, the C++ ABI integration tests that we've been writing are not in the LLVM tree yet, and they should be. It's just something that Timur started on this a long time ago, and he just wrote a makefile and created an SVN repository. And it's publicly available. It's just on some codegoogle.com project hosting site, but it really should be in the LLVM tree because it actually works for GCC as well. And I think it would be good to get something that's not the test suite, but is really designed to do targeted AB integration tests in LLVM,
Right.
even for GCC.
It would be useful in many other contexts.
Yeah.
It's like, I would like to have this.
Yeah.
Right, thanks.
So it looks like most of your examples were 32-bit.
That's true. Sort of that is our initial focus.
The x64 ABI is documented somewhat on MSDN, but it kind of brings a whole new level of crazy.
I'm not as familiar with it. I did check that. I think if you're passing something by value in the first 4 parameters, then you get normal sort of Itanium-like behavior, or maybe not. Okay, don't quote me on that. But certainly, if it's not one of the first 4 parameters, then it's the same thing.
Right.
And yeah, there are other things about the Win64 ABI that are more documented. But the C++ ABI is and sort of the name mangling scheme, record layout. Record layout actually did get more sane. Mm-hmm. There are a lot less cases of just random padding for legacy reasons.
Cool. I'm glad you're looking at that too.
Yeah.
One comment is that we should definitely talk about Inalica because it sounds awful.
Okay. I'm good. We should talk about it.
Yes. Question though, structured exception handling.
So Win64 exceptions are nicely documented. That is one of the things that is documented. Structured exception handling is not something we're really looking at right now. Yep.
So you don't think it's important? It's not an important problem to solve, or nobody uses it, so it doesn't matter.
I'm not sure. What's up?
It's important. It's just we have to prioritize. It'll come up eventually.
Yeah.
Do code bases actually use it?
Yes.
Yeah. To repeat. So we don't think it's that. Basically, we're prioritizing it. And yeah, it does come up. In fact, it is actually used in Chrome. But our approach right now is we have ABI compatibility. Like that's just a funky language feature. Whatever. We can take that to you and compile it with MSVC and link against it. Call it a day. As long as we generate, like ABI conforming, unwind information. I don't know. It's not something I've looked into deeply yet, but we want to fix the miscompiles first.
Here's a silly question. Why do you care about the mangling of static locals?
Because we believe in testing. I don't really care about the mangling of static locals that much. And in fact, I think it's really important to get the case where you just declare a static local in the outer scope correct or right, because that's just important. What's up?
So static locals inside of functions can be inside of inline functions. So if you have an inline function in a header and that has a static local, then
Oh yeah,
you have to operate it.
that was the actual question. Yes.
So you wouldn't link against it, and therefore you would miscompile. So it's a critical
Yes.
problem.
Yes.
I have been eating.
That was a subtle point of this example that I forgot to go over is that static locals at first glance you might think that they are internal names and the names don't matter, but inline functions. Okay, so now the name does matter, and not only that, the name of this matters. This also has a guard variable around it to make sure it's not initialized multiple times. The name of that matters, and that also has this numbering. It's awesome.
Particularly key value of Oxen.
Yeah, Tanium has the same stuff.
So with regards to the debug info and the plugin, what does that mean if you have a stack frame that goes into a standard library that would have been compiled with MSVC?
So there is a fairly good library for reading PDB. Producing PDB is the hard thing. But Microsoft ships like a DIA SDK, which will give you a lot of type information. I don't know about in examining stack frames. That's not something I've ever used from DIA, but So yeah, essentially, like it should be possible to teach LLDB to read PDB, but teaching Clang to produce PDB is much harder. Cool. Anything else? All right.